Alrighty, everyone. Hello and welcome to our live tour of the nighttime sky, a roadmap to the stars. My name's James, and I'm going to be the host of today's guide through our sky. Now, before we get started, I do just want to say a few things. First off, if you guys have any questions during the show, I fully encourage you to put your questions down in the comments section of this live stream, and I will try to answer them as I'm going. If the question is a little, too intensive, it would take a little while for me to explain. I might save it until the end of the show, just for sake of trying to crunch down the show time, because it is a kind of long show. I do tend to ramble. But I will try my best to answer your questions either during the show or after the show. And if I don't know the answer to any questions that you guys ask, I will post them on the Facebook page and on our website whenever I upload the bonus content for this show. If you want to see some of the bonus content that we do for the shows, like last month's show that we did, that's up on the streams section of our website at flyscienceguystarshows.com. So I encourage you to just ask questions. There's no such thing as a bad question. But with that said, I think I'd like to get started with the show. Now, the first set of stars that I want to point out to you guys are these 7 stars over here. And these 7 stars appear to form a pretty familiar figure of the Big Dipper. We have 4 stars in the pot and 3 stars in the handle, our Big Dipper. Now, the Big Dipper is really useful to astronomers because we use it to do something called star hopping. Now, star hopping is where we take brighter, more noticeable stars, and we use them to find dimmer, less noticeable stars. And the Big Dipper is really good at doing this in a lot of different ways. It points to a ton of awesome stars all across our nighttime sky, but there's one particular star that we use the Big Dipper to find that's just a little bit more exceptional. The way that we find this star using the Big Dipper is we take the front 2 stars in the pot of the Big Dipper, and we're going to call these front 2 stars our pointer stars. And we call them that because if we imagine connecting the 2 stars together and going straight out, they point to that very special star. This star, right here. This star's name is Polaris, and Polaris is our North Star. Now, there's a bit of a misconception or a misunderstanding behind the North Star in that we're often led to believe that it is the brightest star in the nighttime sky. Now, here in Stellarium, the program that I use to show these stars to you guys, here in Stellarium, the North Star does look pretty bright. It's probably just making it a little more obvious. But in the real nighttime sky, if you were to go out and use this technique of using your pointer stars to find the North Star, you may actually find that the North Star is actually pitifully dim. No, the North Star is famous for an entirely different reason, and it's given in the name. The North Star is famous because it is a star that is always directly in the north. Now, some people might be a little skeptical because you may have noticed quite a few stars that might be considered directly in the north right now. But Polaris is special. Polaris gets its official name, Polaris, because it's our pole star, a star right above the Earth's North Pole. And as such, it has some pretty interesting consequences that I'm going to show you guys a little later on in the show. But for now, the North Star is part of another recognizable figure, another collection of 7 stars. Since we have a Big Dipper, it would only make sense that we also have a Little Dipper. And indeed, the North Star is at the end of the handle of the Little Dipper. Now, the Little Dipper has just as many stars in it, a set of 7 stars. We have 3 stars in the pot, starting at the North Star, 2 stars going down, or 3 stars in the handle, and 4 stars in the pot, just like the Big Dipper. So I'm sure some people are thinking, well, if the North Star is part of a figure all in of itself, why on earth do we need to use a whole nother figure to find it? Why would we want to use the Big Dipper to find the North Star when we could just use the Little Dipper? We may have noticed some of the... Does the Earth always rotate perfectly on its poles, though? Yes. So, that's a bit of a loaded question. So, in short, yes, the Earth does spin around on its poles perfectly. We'll see in a little bit what that means for our stars. Now, the Earth goes through a lot of complicated movements that makes our poles of the Earth point at different directions in the sky, but that's over a very long period of time. For the rest of your life and your children's life and your great-great-great-great-great-great-grandchildren's lives, the North Star is pretty much going to be our North Star, and the effects of that will be made apparent in just a little bit will also be the same for you and your children. Now, you might have noticed, the reason that we don't use the Little Dipper to find Polaris is because you may have noticed that some of the other stars in the Little Dipper are even dimmer than Polaris. So even in really good viewing conditions, you may find it a little difficult to actually spot the Little Dipper. But the Big Dipper is much more noticeable, containing much brighter stars. You can see the Big Dipper from a lot of different places on Earth. Even when I used to do shows in the bright city of Pittsburgh with all of its light pollution, I could still see the Big Dipper in the sky, pretty much in the middle of Pittsburgh. So as long as you remember to use your pointer stars, they can always help you to find the North Star. So when you do find the North Star, you know you're looking due north, so consequently the south is behind you, east is to the right, and west is to your left. The North Star is the most reliable compass you will ever have, which makes it an excellent navigational star, especially to sailors out on the ocean where they don't have any extra landmarks to help guide their way. Long, long ago, before we had phones or GPSs to tell us where we were on the Earth, people had to rely on magnetic compasses and paper maps, both of which were very susceptible to the harsh conditions out on the seas. For instance, what was a sailor to do if a huge storm brewed up while they were out at sea and knocked all of their navigational equipment off their boat? Well, those sailors, they didn't worry too much, because they knew if they waited until nighttime, they could use the stars up in the sky as a map for down here on Earth. Now, as part of what I do, I love asking people what their favorite constellations are. And sometimes people will tell me that their favorite constellations are the Big and Little Dippers. Now, there's nothing wrong at all with liking the Big and Little Dippers. They are pretty great. But they're actually not constellations. They're what's called an asterism. And an asterism is just a fancy word for a star picture. Aster meaning star, ism meaning shape or figure, asterism, star picture. You can make up as many asterisms as you want. Like, I could look over here and I could play connect the dots with the stars and see the Facebook triangle. I could look over here and see a half-eaten donut. I could look over here and see a 15th century French portrait, if you have the imagination for that. But those are all just asterisms, unofficial. They can be, you can have as many of your own personal asterisms in the sky as you like, but they're unofficial. The difference between an asterism and a constellation is that all astronomers agree on the constellations in the nighttime sky. And the importance of that is it makes a map of the nighttime sky. The reason that the Big Dipper isn't a constellation, even though it's probably one of the most recognizable figures in astronomy, it was probably one of the first figures you learned about in astronomy. Heck, it was the first figure I pointed out in this show. The reason that it's not a constellation is because it used to be and still is different things to different cultures. To us, we see the Big Dipper, we see the spoon, or the ladle. But to English cultures, they see a plow. So here would be the plow, and here's where you connect it to the ox. The Germans, they see a wagon, similarly, where they connect it to the horse, and here's the carriage. And Chinese cultures, they had a completely different star map from the Western Greco-Roman societies, the ancient Greeks and Romans that we get most of our constellations from today. It would be very difficult for astronomers in the past from different cultures to tell other astronomers in other cultures what they find in the nighttime sky and where it's at if no one is agreeing on what they're seeing in the sky or even calling it. It's like if you looked at the map, looked at a road map, for instance, of your own hometown, and you said, this is a mess. I could name these streets better than this person, and so you do. You rename all of the street names in your town. And somebody comes up to you and asks you for directions, and you're all proud of your map, and you want to be a good person, so you help them by giving them directions with your map. But because you renamed all the street names, this other person doesn't have the same map as you. They have a completely different map, so they have no clue what you're talking about in these street names. This was a very similar problem in astronomy until fairly recently, in 1922. In the first meeting of the International Astronomical Unions, a bunch of astronomers from all over the world gathered together and agreed on the 88 constellations that make up our sky today, making a map of our nighttime sky, standardizing the nighttime sky. So that way, no matter what culture you belong to, no matter what language you speak, if one astronomer says the name of a constellation to another astronomer, they always know exactly what part of the sky you are talking about. Now, though the Big and Little Dippers are not constellations themselves, they are part of some of these other constellations. For instance, the Big Dipper is part of the constellation Ursa Major, the Big Bear. Likewise, the Little Dipper is part of the constellation Ursa Minor, the Little Bear. One of the more cuter constellations, I think, and there are many more constellations in our nighttime sky as well, specifically some in the north we can find by using the same trick that we use to find our North Star. So we're going to go back to our pointer stars in the Big Dipper, in Ursa Major, and we're going to use our trick to find the North Star again. So we're going to connect our two dots, our two pointer stars, and go straight out to the North Star. But instead of stopping at the North Star this time, we're going to keep going through, still on a pretty straight line, till we get close to these 5 brighter stars over here, in the shape of a 3. At different times of the night or year, it might look like an M or an E or a W. But this represents Cassiopeia, and she is the Queen of Ethiopia. Hi, Rachel and Brandon. I'm glad you guys could make it. Now, sometimes, not all times, but sometimes when there's a queen, there is often a king. And in Cassiopeia's case, there is a king sitting right next to her. If we use these 2 stars that are part of the sharpest angle in the constellation, they point straight up to a set of 5 dimmer stars in the shape of a house. Some people like to see a squished home plate. I'm very fond of seeing a boxy-headed clown with a party hat on. But this is no clown, this is the king of Ethiopia, Cepheus. Now, I'm sure you guys have noticed that the further we get into the show, the more constellations that I point out, the less these constellations are looking like what I'm calling them. We started out with Ursa Major, and it looks largely like a bear. You have a head up here, you have front legs, back legs. Granted, it has a very long tail for any bear I've ever seen, but you must understand these are astronomers that made these constellations and not biologists. But to their merit, it still looks largely like a bear. But you'd be pretty hard-pressed to see a queen in Cassiopeia or a king in Cepheus. That's because it's not really that important that these constellations should look like what we're calling them. But what's more important is the symbolism, or what it meant to the culture at the time. Again, these being mostly the Greeks and Romans. It was very important that they remembered these constellations relative to seasons, because not only did they use them as a map and a compass, but they also used them as clock and calendar. Depending on the constellations that our ancestors saw on the early evening sky, that is just after the sunset in the west and the first stars start to appear in the sky, depending on the first constellations they saw, they could tell when springtime was coming, and they needed to get their fields ready so they could plant their crops, so they could feed themselves, their families, their village. But they could also tell when winter was coming and needed to bunker down their houses so they could stay warm and survive the cold, cold winters. It's a lot easier for us as humans to remember things when we give it a story and when we give it character. It's a lot easier for us to remember Cassiopeia and Cepheus, the queen and king of Ethiopia, than it is to remember random dots in the nighttime sky and what they're supposed to mean. It's also a lot easier for the ancient Greek children to learn that way too, because that's how children learn, that's how humans learn, through stories and patterns and characters. And those ancient Greek children, they would have had to grow up using these same techniques, using these same constellations to stay fed and stay warm. The next time you have to remember something important, try making a story out of whatever it is that you have to remember, using the details of whatever you need to remember. And see if you can recall that thing just a little bit easier than things that you didn't make a story out of. Now, the trick to this, though, is that you have to make the story as silly as possible. The sillier the story, the easier you'll remember it, as you'll see later on once we see some of these other constellations that the Greeks and Romans made up. Now finally, but certainly not least, snaking in between Ursa Major and Ursa Minor, starting about halfway in between the two dippers, is a long winding tail that wraps around Ursa Minor, away from Cepheus, with a head right up here, is a fairly well-known and one of my favorite constellations, Draco, the dragon. It's a very silly dragon here on Stellarium, but I still like it. Now, all of these constellations that I've pointed out to you guys so far, Ursa Major, Ursa Minor, Cassiopeia, Cepheus, and Draco, all have something in common. They are what are called our circumpolar constellations. And we call them that simply because they appear to make a circle around Polaris. Circumpolar. I know, it's pretty on the nose, but what is interesting about these constellations is what they appear to do as the night goes on, and this is hearkening back to Trevor's question earlier. What I want you guys to do, as I make time go forward, I want you guys to observe how the stars appear to move across our sky as the night progresses. So if we look to our east, stars are rising out of the east, and to our left, stars are appearing to set in the west, just as we expect the sun and the moon to apparently do, you know, rise in the east and set in the west. But the closer and closer we get to Polaris, the stars stop setting, you see? They just begin to skim our horizon. And the closer we get to our North Star, the smaller and smaller of a circle that the stars appear to make around Polaris. Until we get to the North Star, where if I hold my mouse still right next to the North Star, you can see that the North Star isn't really moving much at all. Now, stars don't move any meaningful amount during one person's lifetime, or change very much during one person's lifetime. For the rest of your lifetime, your children's lifetime, your children's lifetime, all of these constellations are still going to look pretty much the same. They don't change that much in just a few human generations. Don't get me wrong though, the stars are moving very quickly out through space, but they're so far away that it's very hard for us to notice that kind of movement. The reason that these stars appear to sail across our nighttime sky over the course of just one night is simply because the Earth is spinning. And because we are standing on Earth, as the Earth rotates, our perspective of what we see in the nighttime sky changes with it. You can think of the Earth spinning as a top. If you've ever spun a top on a table before, you really get it going. As that top spins, the handle doesn't really look like it's moving much at all. I mean, you know the handle is spinning rapidly, but it doesn't really look like it's moving all that much. But the rest of the top appears to very apparently spin around the handle of the top. Well, you can think of the Earth spinning in that same way, and you can think of the North Pole as the Earth's handle. And if the stars are simply appearing to move because our perspective on Earth moves, as the Earth spins, all of these stars will appear to spin around Polaris, but Polaris, being right above the Earth's air quote handle, won't appear to move very much throughout the night at all. So I just want to emphasize that the stars moving across our nighttime sky is not them moving, they're just appearing to imitate how the Earth moves. Now the problem with that bit is now I have to set us back to night. Oh, that actually worked out perfectly, kind of. So, the North Sky is an excellent place to practice your astronomy. All these constellations that I've shown to you so far are up all year round. Now, they'll be at different places throughout the year. For instance, this is how the sky would look tonight in about 30-ish minutes or so. But if we looked at this same time, the same nighttime sky 6 months from now, the Big Dipper appears to be on the other side of the North Star now. Our pointer stars still point towards Polaris, but the Big Dipper appears to be on the other side of the Little Dipper. But all of these constellations we see 6 months from now are still up in your sky. So these constellations are perfect for you to practice looking for constellations and practice seeing stars in the nighttime sky. That way it stays familiar to you all year long. What's really interesting though, and my favorite part of the show, are what are called our seasonal constellations. Constellations that do change throughout the year, or different constellations that you see throughout the months. The very same constellations our ancestors used to predict the oncoming seasons. Now, to see those constellations, we're just going to have to turn around in place and look towards our south sky. Easy as that. Still 8 o'clock, still tonight, and I'm going to show you guys some of the constellations that we can only see around this time of year. Now, the first set of stars that I want to point out to you guys are directly above our heads. And this is just a reminder for any people that jumped in after the intro. If at any point you guys have any questions about things I talk about, just feel free to comment in the live stream comments section, and I'll try to answer your question as I'm going. And if it's too big of a question, then I'll just simply answer it at the end of the show. But I'll try my best to answer all of your guys' questions if you post any. And if there's any questions that I don't know the answers to, then I'll just do some research after the show and then post them on the Facebook page as soon as possible. So the first set of stars that I want to point out to you guys, if you're facing south, is pretty much directly above your heads. And it's these 3 stars right here. These 3 stars form another asterism, so not a constellation, but an asterism called the Summer Triangle. And the Summer Triangle is called the Summer Triangle not just because it's a triangle up during the summertime. As we can see, it's officially fall, and the Summer Triangle is still directly above our heads. No, the reason that it's called the Summer Triangle is because during the early summer months, so let's say June, the Summer Triangle will rise out of the east just as our sun sets in the west. And the Summer Triangle will dominate our nighttime sky all throughout the night until it finally sets in the west just as our sun rises in the east. So that's why it's called the Summer Triangle. It's one of those asterisms that our ancestors used to help them say Well, this must be the middle of fall right now because our summer triangle is halfway across our sky. And we know that fall is halfway in between summer and winter. So the summer triangle in fall is halfway across our sky when the sun sets. So the three stars that make up our summer triangle are Vega. Down at the tip of the triangle, we have Altair. And up at the left corner of the triangle, we have Deneb. Vega is the brightest star in the constellation of Lyra, the harp. Altair is the brightest star in the constellation of Aquila, the eagle. And Deneb, which is an Arabic word which roughly translates into tail feather, it's fitting because it is the brightest star and tail feather of Cygnus, the swan. Now, earlier I talked about how cultures from all around the world had stories about the stars, and they were either used to predict seasons, to teach lessons, or they were just used to make a stage of our stars. This was their entertainment. They didn't have television, they didn't have radio all the way back when these constellations were being conceived. What they had for entertainment was their imagination and the stars. One of my favorite stories is from the Chinese culture, and it's a story that was used to commemorate a holiday of theirs called Qixi. And Qixi is like a Chinese Valentine's Day. Now, the story that they told involved Cygnus, Vega, and Altair. Vega, in the story, was named Jinu, and Altair was named Niulong. Jinu was a beautiful weaver goddess. Her job was to weave colorful, beautifully colored clouds in our sky. Pink clouds at sunset, rainbow clouds after a fresh rainfall, white clouds on a clear, well, not a clear summer day, obviously, but on a summer day. That was her job. But she was young, and she got very bored of just being up in the heavens all day weaving colorful clouds. So she decided that she wanted to cause a little mischief. So she came down to Earth to just rustle some feathers. And when Jinu did come down to the Earth, Niulong caught sight of Jinu. And Niulong, who was just a simple farmhand, thought that Jinu was the most beautiful woman he had ever seen. And he fell instantly in love with her. Somehow Niulong convinced Jinu to fall in love with him as well, and they were just having a ball of a time. They were having picnics, they were smooching. Oh, it was a grand old time. But Jinu's mother eventually found out that her daughter had left her post. And what more, she found that Jinu was canoodling with a mortal, and she didn't like that, not one bit. No sir, not her. So Jinu's mother came down to the earth and demanded that Jinu get back up to the heavens and continue weaving colorful clouds. Well, Jinu was caught and she didn't want to get in any more trouble, so she did as her mother said and she went back up to the heavens to continue her job of weaving clouds. And this absolutely devastated Niulong. He was incredibly heartbroken. Niulong was so distraught that his ox began to speak to him. You know how oxes do. You walk near a pasture really sad and they just come up, they won't start yapping at you. So this alarmed Jinu. His ox had never spoken to him before. But his ox had some words of wisdom. His ox said, "Niulong, if you sacrifice me and don on my pelt, you can ascend to the heavens to be with Jinu once again." If an ox were to speak, I'd imagine he'd sound like that. Well, Niulong really liked his ox, but he liked Jinu more. So Niulong reluctantly did as the ox recommended, donned on his pelt, and began to ascend to the heavens to be with his loved one. Well, Jinu's mother saw what Niu Long was trying to do, and she really didn't want the lovers to be together. So Jinu's mother took a hairpin out of her hair and ripped the sky in half, creating the Milky Way. Now, scientifically, that is not how the Milky Way was formed. What we see as the Milky Way is just the collection of hundreds of billions of starlight. And we're looking edge on at our galaxy in this view. But in the story, Jinu's mother, her hairpin ripped the sky in half to keep the the lovers apart. And it worked. They weren't able to see each other. They were separated by the Milky Way. And so they were absolutely devastated because they still couldn't be together. But it's said that one night out of the year, on the 7th day of the 7th month of the Chinese lunar calendar, all the magpies take pity on the two lovers and fly up to the heavens to form a bridge across Cygnus's wings, where the lovers could meet together and be together for 1 year out of the night. That's one of my favorite astronomical stories from cultures. There are a ton of different ones, and maybe someday I'll make a show all about the different stories. Maybe someday soon. That sounds like a good show. Now, all three of these stars have their special claims to fame, but there's another star, which is one of my favorites, in the Summer Triangle, that isn't quite as noticeable. And if you do notice it, it's very unassuming. That favorite star of mine is right here, and its name is Albireo. And Albireo, to the naked eye, is a pretty dim star. Even if you were in a bright area, you might even overlook it. But if you had a good pair of binoculars or a low-powered telescope and you looked at Albireo, you would find that it wasn't just one star, but two stars. Albireo is what was once thought of as a binary star system. A binary star system means having two stars orbiting around one another, much like how the Earth and the Moon orbit each other, or the Earth and the Sun orbit each other. Now, it was later pretty much agreed upon that these two stars are actually not orbiting each other. They're just what's called an optical double, meaning that they look close together from our perspective in space, but are actually not orbiting one another. We think that they did come from the same stellar nursery, the same cloud of gas and dust as formed from gas and dust in space. We think that they formed from the same gas cloud, but they're not actually orbiting each other. But I still like bringing it up because there's something a little more noticeable about these two stars when you have a telescope, and that's their colors. These two stars in Albireo are very apparently different colors. A lot of the time, we don't even think about stars having color. When we look up into the nighttime sky, we often just see pinpoints of light, which is understandable. We as humans are very bad at detecting color in low light situations. But if you can notice a star's color, you can learn a little something about that star without needing any high-tech or special equipment. If you can notice a star's color, you can learn a little bit about what its temperature is. Stars are what are called black body radiators. Depending on the amount of heat they give off, the amount of energy they release, their color will reflect that. So red stars, like Albireo A, are the coolest among star colors. They can get as low as 5, even down to 3,000 degrees Fahrenheit on the surface of a star, while still being able to emit light. But blue stars, like Albireo B, are the hottest among star colors. They can get as hot as up to 40, even 60,000 degrees Fahrenheit on the surface of the star. Now, when I say the surface of a star, I don't mean the kind of surface like here on Earth. You couldn't stand on a star. Stars are just hot, glowing balls of gas and plasma out in space. When I say the surface of a star, I just mean the outermost edge of the star, what's called the photosphere of the star. This is where the star's light, little packets of photons that we use to perceive light, that's where that light leaves the star. That's where we notice the star's color. So a lot of times when astronomers talk about the temperature of stars, they're usually just talking about the photosphere of the star, the outermost edge. Because the cores of every star can get up to millions of degrees in temperature from the intense pressure of gravity pushing down on the core of the star. Our sun is considered a yellow star. If you were to see the sun from out in space, it would appear to emit more of a whitish light. But because of its temperature, around 10,000 degrees Fahrenheit, we consider it a yellow star. So there is some kind of wiggling room in there. But the next time you go out, hopefully tonight if it's clear, and if you're younger with adult supervision, next time you're out and you see some stars, try to pick out some colors of stars and compare them to each other. Figure out which stars are cooler compared to other stars. Now, the next set of constellations that I want to show you guys are below the Summer Triangle, and we can use the Summer Triangle to help us. If we imagine Altair as the tip of the triangle, Summer Triangle, points straight down to a thick V-shaped constellation down here. This thick V-shaped constellation represents Capricornus, and he is a mergoat. Part goat, part fish. This is where it goes back into it's easier to remember things when they're ridiculous. That is very unfortunate that it's not clear tonight. But don't worry, because everything that I show you tonight, you'll pretty much be able to see all throughout the month of October. So you'll have plenty of opportunities to see the things that I'm showing tonight. And it's going to look pretty much the same. One thing that I do want to mention, though, since I do bring that up, I say pretty much the same. Right now, our stars do appear to move across the sky and set earlier and earlier every night. And I'll explain why that is in a little bit, just so I don't get away from myself. But this is how the Summer Triangle is directly above your heads tonight and probably the next couple weeks. But towards the end of October, let's say October 31st, it's not going to be necessarily directly above your heads. It's gonna, there we go. It's going to be a little more towards the western sky, because as the months go on, the stars do appear to set earlier and earlier. And again, I'll explain why that is in just a second, but either way, all these things will still be up all month long, so you'll still get to flex your astronomy knowledge to your friends anytime this October. Now, if the name Capricornus sounds familiar to you, it probably shouldn't be too surprising, because Capricornus is one of 12 of what are called our zodiacal constellations. And our zodiacal constellations, well, let's name off a few more first. To the right of Capricornus, we have what kind of looks like a teapot shape figure over here. See, here's the handle, here's the body of the teapot, here's the spout, and here's the lid of the teapot. Now, this figure is another asterism called the Teapot of Sagittarius. And it's called that fittingly because it is part of the constellation Sagittarius, the Archer. Now, during my time at Clarion University, when I directed their planetarium, I did shows with a wonderful person named Gary Purington, and he would often do, we would often have him do the southern sky, I would do the northern sky. It's kind of a tag team thing. And so he'd always talk about Sagittarius. And one of my favorite things that he used to say about Sagittarius is he would say, you know, they always say Sagittarius the archer. I don't know about you, but that's not the most prominent thing that I notice about Sagittarius. If I would have seen Sagittarius coming down the street with a bow and arrow, I wouldn't say, hey, look at that archer over there. I'd say, that man's half horse! Oh, Gary was a treasure. But Sagittarius is officially called the Archer. Now, to the right of Sagittarius, we have a bright red star near to the left of a string of 3 stars that kind of looks like Orion's belt sideways, but it's not Orion. It is Scorpius, the Scorpion. Going back to Capricornus, going in the other direction, I'm going to be frank with you guys. I am really bad at drawing out this next constellation, so I'm just going to click on it and show you. To the left of Capricornus is Aquarius, the water bearer. To the left of Aquarius, we have a circle of stars here that goes down into a V shape, and then back up to another circle of stars up here. And this is Pisces, the fish. And to the left of Pisces, we have a kind of long line of stars here that kind of looks like it has a crook at the end of it. And astronomers would look at this constellation and they said, yep, that's a goat. Aries the ram. Ram. I always say goat. Goats and rams are not the same thing, but I'm not a biologist. So all of the zodiacal constellations, as we can see, appear to make a line across our nighttime sky. But it's not just any line, it's a very special line. This line is called the ecliptic. And the ecliptic is the apparent path that our sun appears to take across the sky throughout the year. So we see different months labeled here on this line. These dictate where the sun would be at a certain time of year. So December 1st, the sun would be here in Scorpius, the Scorpion. January 30th, the sun would be here in Capricornus, the Mergoat. And September 15th, the sun would be smack dab right in the middle of Pisces, the fish. And our ancestors, they noticed this. They noticed the sun was appearing to track a certain way across the sky. So what they did something that was actually pretty difficult, because it's not really easy to notice what constellation our sun is in front of, because of course when the sun is up we can't see any of the stars. Whoops, that's not the right setting that I wanted. Okay, we can't see any of the stars when the sun is up. Our sun's light ends up refracting in our atmosphere, scattering, causing it to glow that romantic blue we often think about on a clear summer day. So what they did was they watched the sky every night, and they waited for the sun to set. And they waited to see what stars immediately chased after the sun in the early evening sky after it set. And so they did this for... Let me set this back here. They did this for the next night, and the next night, and the next night, and they saw that the stars were setting earlier and earlier as the sun was appearing to trek across them, moving in front of them. And they did this for years. It was painstaking work, and it was tough work. But they eventually got their findings to be what they thought was pretty reliable, and then they made 12 constellations to match their 12 months of the year. These are Greek and Roman constellations. And the Greeks and the Romans use the Julian Gregorian calendar, which both have 12 months out of the year. In fact, we still use the Gregorian calendar today. And so they made these 12 constellations to match the 12 months out of the year, and the zodiacal constellations were born. Now, this was kind of the idea behind astrology. At one time, astrology was astronomy. Every court had a court astrologer that would recommend certain actions for the king to take because the sun was in a certain constellation. But none of that's true. They also used to think that human behavior was based on what constellation the sun was in front of when you were born. Now, back then, humans didn't really know much about astronomy, let alone psychology, and so this was a big thing. But as we learned more, we knew that the sun, what constellation the sun was in front of had no impact on you as a person. And in fact, one of the lesser known things is that the dates on normal horoscopes, normal horoscope calendars, are not actually correct anymore. They were correct whenever the ancient Greeks and Romans, whenever they first made these zodiacal constellations, but the Earth goes through a lot of complicated movements. And since the several thousand years ago when they came up with the zodiacal constellations, the ecliptic here has shifted to the right about a whole constellation. So the date you were born on was probably in front of the constellation to the right of whatever your horoscope tells you. So there's really no basis behind horoscopes. I know it is fun to look at horoscopes. I get that. And I'm not saying that you shouldn't do that. Just, don't get had by the ideas of astrology. And astrology and astronomy, one big thing to point out is they're no longer the same thing. Astrology and astronomy are separate entities now, since several thousands of years ago. Now, the sun is not the only thing that appears to trek across our zodiacal constellations. The ecliptic is also the close apparent path of our moon and planets as well. So this is the ecliptic that I've just brought up, and these are the orbits of our other 7 major planets, not counting Earth, of course, because we are standing on Earth. But we can see that the rest of our planets appear to make a pretty straight line across the zodiacal constellations, and they're always in front of a zodiacal constellation. So you would expect to see one of these planets at some point throughout the year in front of one of these constellations. And in fact, you can see you can see a few constellations up at 8 o'clock this evening. Now, here in Stellarium, it's a little obvious which of these objects are planets and which ones are stars. But in the real nighttime sky, it might not be that obvious. So I want to teach you guys how to find out if what you're looking at is a planet or a star when you look up into the sky. There's 2 questions you should ask yourself. 1, is what I'm looking at in a zodiacal constellation? As we saw, the planets will always appear to be in front of a zodiacal constellations. Again, these are the orbits, so this is the only place you will find these planets. So if the answer to that is yes, what I'm looking at is in a zodiacal constellation, then you might be looking at a planet. But if the answer is no, what I'm looking at is not in front of a zodiac constellation, then you're probably not. But you're still also not guaranteed that you are. So you should ask yourself this second question. Is what I'm looking at twinkling? Oh, this is the best part of the show. This is where I show off my excellent artistic skills. Stars put out a tremendous amount of light. But they're very, very far away from the Earth. So by the time a star's light travels across our galaxy to the Earth, very little of that light actually makes it here. You can kind of do an experiment to understand this idea better. If you take a flashlight and you go outside, again with adult supervision if you're younger, You take a flashlight, you turn it on, and you point it in a direction where it can go for a while without hitting any houses or trees. And you'll notice that the light from your flashlight kind of appears to spread out a little bit. It appears to get thinner, and it appears to get dimmer, and it doesn't really illuminate much anymore. This is a very similar thing, or the same thing that's happening with these stars. The star is so far away from the Earth that very little of the light actually gets there. And when it tries to get through our atmosphere is filled with water particles, water droplets rather, and dust particles, and oxygen. Oxygen's gonna be purple because I don't have any other colors. And so as the sun's light, or as the star's light comes through, it bounces off of all of these particles in our atmosphere. And when it reaches our eyes, it keeps coming in at different directions because all of these particles are constantly moving around in our atmosphere. So as it kind of bounces off and enters our eyes in different directions, it kind of looks like it's twinkling or dancing a little bit. It kind of looks like it's a little over here and a little over here. I love giving experiments for people to do, because I never really like the idea of, even if it's a well-known scientist, everyone makes mistakes. So if there's ever anything that you're like, that doesn't make a whole lot of sense, do an experiment with it. Find an experiment you can do on a larger scale. Never take anyone's word for anything. So anyway, an experiment you can do to kind of see something similar with this is get a half-filled bottle of water in clear plastic or whatever, as long as light can get through it easily, and turn on a flashlight again and put it behind this half-filled bottle of water. And then shake up the bottle of water, really good. Shake it up so all the water in the bottle sloshes around. And as the flashlight is going through the bottle and bounces off this sloshing water, it'll kind of look like your flashlight light is dancing. And that's very similar to what's going on here. However, planets are a lot closer to us than stars are. And so planets don't really give off their own light. However, if you take a planet, let's do a red planet, let's do Mars. You take Mars, for example, and you take our sun. Sun's over here. And the Earth is right here. When our sun's light reaches Mars and then bounces off of it and gets reflected to Earth, a lot more of that light ends up actually reaching here. So its light is not as affected by our atmosphere, and it doesn't really appear to twinkle all that much. So planets don't really appear to twinkle as much as stars do in our nighttime sky. So if you want to find out if what you're looking at is a star or a planet when you go out tonight, just ask yourself those two questions. Is what I'm looking at in a zodiacal constellation? And is what I'm looking at twinkling? If the answers to those questions are yes and no respectively, then what you're looking at is more than likely a planet. And we have 3 planets up right now in our sky. And we'll start over here in Sagittarius. This is very close to the summer triangle. So the summer triangle almost actually points down to these planets tonight. And we'll start with this guy right here. This is the largest planet in our solar system. Maybe something you can answer at the end, but I've noticed a red star in the east. You know what I'm looking at? Yes! And I will answer that in a little bit because that is coming up. Sign up for art. Sign you up for art lessons. Oh, there will be plenty of more drawings. I'll give you some pointers to my awesome art, and it's not done yet. Boy, howdy. This planet right here, this it'll look probably the brightest out of these two in Sagittarius, is our largest planet in the solar system, Jupiter. Jupiter is impressively large. Again, the largest planet in our solar system, and it's the first of our gas giants. Gas giants aren't like Earth. They don't have surfaces that you could stand on. They're closer to stars than they are to terrestrial planets because they're just big balls of gas and dust out in space. Galileo was one of the first people to look at Jupiter. And when Galileo looked at Jupiter through his telescope, he noticed, and this is one of Galileo's drawings, I can't take credit for this one, he noticed that there appeared to be almost little stars almost around Jupiter. He looked through his telescope and he got a little bit of a chuckle. He was like, oh, that's pretty cool. These stars look like they're awfully close to Jupiter. That's really neat. And so he got done drawing it that day, and he had dinner, went to bed, woke up the next day, did his chores, and then nighttime came and he wanted to look at Jupiter again, and he did, and he was like, hold on a second. This isn't right. These stars appeared to have moved. They're not in the same place as they were last night. And there are plenty more drawings. I don't have all of his drawings, but they exist somewhere online. But he has a bunch of different drawings, and he very carefully looked at Jupiter and these apparent, what he thought were stars, throughout the year. And he eventually concluded that what he was looking at was not stars, but Jupiter's moons. And so these 4 brighter stars that you're easily able to see with a low-powered telescope or a good pair of binoculars are now called the Galilean moons. Some other things that he noticed on Jupiter was also this great red spot. The great red spot on Jupiter... Come on, mouse. The great red spot on Jupiter is a giant anti-cyclonic storm, meaning it kind of spins counterclockwise, very similar to hurricanes that we have here on the Earth. But unlike hurricanes we have here on the Earth, it's about 2 to 3 times more powerful than any hurricane Earth would ever have, and it's about the size of the Earth. The Great Red Spot on Jupiter is 1.5 times the size of the Earth. Now, you need a bit more of a powerful telescope to really notice the red spot on Jupiter, but when you can notice the red spot, it's a good comparison to just how, it's a good contrast to just how large Jupiter is. Because I've now superimposed, if you blinked and missed it, I've superimposed the Earth onto the Great Red Spot. This is about how big the Earth is compared to Jupiter. It is not only an incredibly large planet, it is an incredibly massive planet. Now that may have seemed redundant, as if I said that Jupiter was large twice, but I didn't. Mass and volume are not the same thing, though we often use the term massive to say that something is large in everyday conversation. Mass is what makes something up. It's what gives something weight. It's what gives me weight. It's what gives you weight. It's what gives my mouse and my phone weight. Jupiter is so massive, in fact, that it has more than twice the amount of mass of all of the other planets, their moons, and the asteroids in our solar system combined. It is an incredibly massive planet. Now, the Great Red Spot, however, one thing I did want to mention is that it's also a storm that's been raging for maybe about 300 years at least. I say maybe at least because one of the first mentions of the Great Red Spot was in Galileo's journals, but it's kind of up to scrutiny because way back when, even the best telescopes that Galileo used, from what I could find, are only about as powerful, or were only about as powerful as the lowest grade telescopes we have today. So it would have been very hard for him to notice the Great Red Spot. Not impossible, because the Great Red Spot would have been a lot larger back then, because the Great Red Spot is actually shrinking, appearing to shrink. I think recently we found out that it's been slowing down a bit, but if it were to continue to shrink, it might disappear. Now, another storm might take its place and rage for another hundreds of years, but the red spot could disappear one day. And Mary, boy, is that a question I love. I love gravity. Gravity is my favorite thing about astrophysics and astronomy. That is absolutely correct. Mass does affect gravity. So when something has enough mass, it has more gravity than something else. So our moon orbits around us because it has less mass than the Earth does. So the moon is overtaken by Earth's gravitational force because since the Earth has more mass than the moon, it has more gravity. Don't know if you said it already, but do we know what causes the red giant spot to keep going as long as it has? It's mainly just the fact that Venus, it's likely mainly just because the fact that Venus doesn't have a surface, so there's not really a lot of drag that ends up killing the storm. So, so the reason, here on Earth, we get, hurricanes mainly because of, out on our oceans, there are, currents that, now, I'll answer this the best I can because I'm not completely fluent on, meteorology. However, one thing I can tell you is that our hurricanes originate out on the oceans, mainly because of how air currents work out on the oceans. And the oceans kind of fuel the drive of hurricanes. However, when hurricanes get onto Earth, the airflow completely changes. And there's a lot more drag that goes on, and eventually the hurricane ends up puttering out. However, Venus has no such surface for it to putter out on. And so it's being driven by these bands of clouds on Jupiter, which are rising and sinking cloud systems. Some are going this way, some are going that way, and it's just kind of keeping this drive going for this hurricane. Now, there are probably things, because it's just a gas giant, it is still dynamic, and it still does change, which can affect the storm as it drifts to different areas. But it's a lot longer lasting, likely because there is no surface to impede this airflow. And then to finish up with Mary's question, whenever something has more mass, it will have more gravity. Now, I'm just going to very briefly do this, but how we define gravity is by masses of objects over their radius. Don't worry about this. So we have the Earth's mass here, the Moon's mass here, and what this defines is how much gravity is being put on the Moon. Now, if the Earth had less mass than the Moon does, then this gravity would be affecting the Earth, and we would be going around the Moon instead. Which is also why everything in our solar system goes around the sun. Because though Jupiter makes up, has about twice the amount of mass of all of our other planets combined, the sun still makes up 99.98% of all of the mass in our solar system. So everything is attracted to the sun. If the sun wasn't there, closer things to Jupiter would be attracted to Jupiter. So it's pretty much just an arm wrestling contest of who has more mass, and then that object gets the dominance, and everything ends up going around that object. I hope those answered those questions. If not, I can try a little better towards the end of the show. Now, where was I? I was talking about Jupiter. I was talking about how Galileo likely saw the Great Red Spot. but it's up to scrutiny. One thing, though, that Galileo did see are the rings of this next planet. Probably one of the most beautiful planets in our solar system. Oh, wait. I almost brought up the image of it. I don't want to bring up the image of it. I want to bring up a new program that I'm adding to the show. Bum bum bum! Open space. Saturn. When Galileo looked at Saturn, he called it a planet with ears, because at a certain distance away, through his telescope, it looks like Saturn. Down here is a telescopic view of Saturn, what you might see through a lower powered telescope. To him, it looked like it was a planet with ears. In his drawings, he thought that they might have been moons that were going around Saturn. A few years later, he noticed that, or he came to the conclusion, well, they obviously aren't moons, but he didn't know what they were. He actually didn't find out that they were rings. It was another astronomer, Huygens, quite a few years later, that discovered that. But Saturn's rings are always a lot of fun to talk about, because they're all of our gas giants do have rings, but none like Saturn. Saturn's are super obvious, and you can see them through even low-powered telescopes. Saturn's rings, from the edge of the sphere, because Saturn is also a gas giant, it doesn't have a surface, so from the edge of the gaseous sphere of Saturn, the rings extend out about 175,000 miles out from its surface, which is why they're so obvious to us in a telescope. However, the rings are just a few yards thick. If you were to shrink Saturn down to the size of a standard football field, the rings would be thinner than a human hair. And so when Galileo was looking at Saturn, he noticed that at a certain point, after a few years, he noted in his journals that the moons, what he thought were moons, appeared to disappear. And that's because he was looking at Saturn edge on. This is how thin Saturn's rings are. Incredibly thin. And then a few years later, he kept studying Saturn, and Saturn was at a different place in its orbit, and he could see the rings of Saturn again. Now, another one of my favorite facts about Saturn is that if Jupiter is our most massive planet in our solar system, but Saturn is the least dense planet in our solar system. Saturn, density is, if mass makes something up, density is how much stuff or mass makes up a certain object's volume, its size. So Saturn is so not dense that it is less dense than water. Meaning that if you had a bathtub big enough and you plopped Saturn inside of it, and, well, you got a bathtub big enough, filled it up with water, plopped Saturn inside of it, Saturn would float. The whole planet of Saturn would float on that water, making it like our solar system's very own rubber duck. So both Jupiter and Saturn are excellent telescope targets, and I absolutely recommend taking a pair of binoculars and trying to spot... I don't need to bring that up yet. Trying to spot Jupiter's moons, which you can see, it's a little backwards than how I have Saturn. Here is the telescopic view of what you would see with a low-powered telescope. So you can see the moons of Jupiter with a low-powered telescope, and you can see the rings of Saturn with a low-powered telescope. Both I highly recommend. Now, another planet that's in a good position for viewing, because it's currently in what's called opposition, is over in the east. So we have... I'm going to get this other mouse out of here because that's confusing. So we have Jupiter and Saturn in Sagittarius, the Archer. Over here, rising out of the east at around 8 o'clock, is a brighter red object, which is our red planet, Mars. So let me fly us to Mars. Now earlier I talked about stars' color representing their temperature. So stars appear red because they are black body radiators and they are very hot. But Mars is red not because of its temperature. Actually, Mars is very, very cold. It's a cold desert world covered in iron oxide. And if you've ever seen a pipe laying out on the lawn after rain, or you left a bicycle out too long, you've seen iron oxide before. Iron oxide is more commonly known as rust. Mars is red because it is covered in rust. It is like our rust ball out in space. It's so cold because its atmosphere is so thin. Now, though Mars's atmosphere is mostly made up of carbon dioxide, which is a very potent greenhouse gas, it's a gas that traps heat in planets, its atmosphere is actually very, very thin. So it can't really retain any heat from the sun, or a lot of heat from the sun. But that doesn't make Saturn any less cool. There are some notable features on Saturn in terms of its topography. Saturn boasts the largest canyon in our solar system, Valles Marineris. Valles Marineris is the largest canyon in our solar system, being about as long as the continental United States is wide, and about as wide as our Grand Canyon is long. And in some parts, it's about 4 miles deep. So, the thing is, though, that this canyon was not carved out the same way as our Grand Canyon was here on Earth. Our Grand Canyon here on Earth was carved out from water over... Did I say Saturn? I did not mean to say Saturn. Any time I said Saturn when I was looking at Mars, I meant Mars. Yes, Mars has the largest canyon in our solar system. Now, the Valles Marineris, though, Mars's canyon was not carved out by water like our Grand Canyon was. Mars, once upon a time, probably looked a lot like Earth in that it was covered in water, and it had tectonic activity, meaning it had tectonic plates that shifted around. The reason that our continents move around on the Earth is because of our tectonic plates moving. Here on Earth, we have 7 major tectonic plates. I don't know how many tectonic plates in all, but we have 7 major tectonic plates. Mars only had 2. It only had the northern hemispherical plate and its southern hemispherical plate. So here on Earth, our tectonic plates move around, and this causes earthquakes, it causes volcanoes, it causes, for instance, the Marianas Trench is caused by tectonic plates coming together and dipping under and creating huge valleys, or huge underwater pits. Mars, since it only had 2 tectonic plates, when they moved, they essentially ripped the planet open. And Mars is about 1/4 the size of the Earth, or 1/3 of the size of the Earth. So it once had a molten core that allowed it to have moving tectonic plates, but Mars cooled a lot faster. And so its core is a lot less molten now. It doesn't have as much tectonic activity, if any at all. And so all the water that was left over on Mars kind of rushed in and solidified the ground, creating a pit that's about 4 miles deep. There are some other canyon structures that were carved out by water before the oceans of Mars boiled away. But the main part of it, this here, was caused by the tectonic plates ripping the planet open, which is just so cool to me. Now, Mars doesn't just boast the largest canyon in the solar system, it also boasts the largest volcano in the solar system as well, Olympus Mons. Olympus Mons is about as wide as the entire country of France and is 3 times taller than Mount Everest. Now, this view of how tall Mars is compared to Mount Everest makes it look very, very steep. However, like I said, it's about as wide as the entire country of France, so if we land down on Mars, we can see that it's actually very, very shallow. That's because it's what's called a shield volcano. Most of the time when people think of volcanoes, they think of large smokestack volcanoes that end up going in a giant pyroclastic fire show or fireworks show when they erupt. Shield volcanoes are made a little differently and a bit less violently. Shield volcanoes end up starting as kind of like a hole in the ground. As lava comes up from the center or from the upper mantle of a planet, that lava ends up hitting the surface, and if there's a place for it to escape out of, or it carves a place to escape out of, it ends up just kind of bubbling up, and the lava spreads out, and then that lava hardens, and then through that same hole, more lava comes up, and that spreads out and hardens, and it bubbles and bubbles and hardens until we get this kind of lump, this sorry excuse for a hill. I say sorry excuse. It's still the largest volcano in the solar system. But this is another good example. So, like I said, it's about 3 times taller than Mount Everest, and we can see how thin Mars's atmosphere is. This volcano almost sticks out of Mars's atmosphere. It is that tall, and Mars's atmosphere is that thin. Mars is mostly covered in shield volcanoes, probably because it was a lot smaller than Earth, and it probably wasn't as hot in the center of the planet, and thus didn't have as much pressure pushing things out. So you mostly just get fields of shield volcanoes rather than small or tall smokestack volcanoes. Like their real name is composite volcanoes. I just describe them as smokestack because that's easier to imagine. So those are some of the planets that you'd be able to see earlier in the evening. Now, the last planet that is going to be up and has gotten a lot of news recently doesn't come up until the early morning, around 5 o'clock in the morning. This planet right here. This is one of my favorite planets, Venus. I would show you on open space, but they don't have Venus's atmosphere on open space, and so it's not a good representation of Venus. But Venus is a really interesting planet. It's the closest planet to the Earth, so it's one of the brightest objects that you can see in the nighttime sky. It would be very obvious to anyone who goes out just before sunrise. They would see this bright object rising out of the east, and it's actually been given a misnomer of the evening star or the morning star. But again, it's a misnomer because it's not a star. It is the planet Venus. And Venus is the hottest planet in our solar system, and one of the strangest planets in how it moves. So, to start off, most of the planets in our solar system. Here comes some more art. So here's our sun, and I'll draw Earth out here. And I'll draw Venus right here. All of the planets in our solar system go around the sun counterclockwise. as so. And on top of which, most of our Venus does go around counterclockwise too. And most of our planets spin on their axis counterclockwise as well, which is why our sun rises in the east and sets in the west, because of how the Earth spins on its axis. However, Venus, though it does go around our sun counterclockwise, does not spin counterclockwise. It spins clockwise on its axis. Now, the way that our solar system formed, it's very likely that Venus was spinning counterclockwise when it formed during the early formation of our solar system. But the early solar system was a violent place, and it had a lot of stuff fighting for supremacy in certain orbits. And so it's thought that Venus did form spinning counterclockwise, but there were some nasty protoplanets or big asteroids that were fighting for Venus's place in the solar system, and one, even maybe two, objects slammed into Venus in such a way that it caused Venus to flip upside down. And so before it flipped, it was spinning counterclockwise. Now, just because it was flipped upside down doesn't mean that it stopped spinning in the way it did. So because it flipped upside down, it's now spinning clockwise. It's kind of a hard thing to grasp just taking my word for it, but if you have maybe a fidget spinner, or you have some sort of disc-like object that you can spin in your hands and then easily flip upside down, you can notice that when you spin an object one way and then flip it upside down, it's now spinning in the opposite. It looks like it's spinning in the opposite direction that you started spinning it before you flipped it upside down, but it's still spinning in the same way. You just flipped the axes that it was spinning around. So this isn't really an easy thing for me at the moment to feel like I've successfully made it understandable. So I really recommend finding some way to play with this idea yourself. And again, one of the easiest ways I've found so far that's really manageable is finding a fidget spinner and then spinning it in one direction and then turning it upside down. But that same thing happened with Venus. And so now we have a planet that spins clockwise rather than counterclockwise like most of our other planets. And because of that, Venus now spins a lot slower than any of our other planets. So here on Earth, it takes 365 days to go around the sun once. So that means by the time the Earth has moved around our sun one time, the Earth has spun around on its axis 365 times. Venus goes around the sun in 225 of our days. So Venus gets around our sun by the time the Earth has spun around its axis 225 times. However, a Venetian day, how long Venus takes to spin on its axis, is about 112, 113 days. That might not be 100 accurate, I'm just back of the enveloping. It takes Venus, Venus only spins around twice on one trip around the sun. So any given point on Venus is pointed towards the sun for half of its year. So it gets very, very hot on Jupiter, mainly because of that reason, but also because Venus is shrouded in a thick atmosphere of carbon dioxide gas and sulfuric gas. Very potent greenhouse gases. So we call them greenhouse gases because it works kind of similar to a greenhouse. Sunlight can easily pierce through these thick clouds around Venus. And when that sunlight hits the surface of Venus, it gets absorbed and re-radiated as lower energy light, or heat. Much like on a hot summer day, when you leave your car out, when it's not in the shade, sunlight can come in through the window. Sunlight can easily get through your car window. But when that turns to heat, it can't get back out of your car's window. So it gets really, really hot by the time you open up the car because all that heat gets trapped inside. That's pretty much exactly what's happening on Venus. So that sunlight comes in, gets trapped, and then more sunlight comes in and that gets trapped, and it builds and builds and builds until we have Venus at the temperature it is today. Nearly 900 degrees Fahrenheit, day and night. On top of which, like I said, it has sulfuric gases in its atmosphere. It also rains sulfuric acid onto Venus's surface. It's a very hostile planet, not a place that anyone would want to go vacationing, let alone live there. So Venus was never one of the top contenders for us to think it would have life on it. However, Venus has been in the news recently because we've been noticing a lot of a specific type of gas in its upper atmosphere, phosphine. Now that might not really mean too much from the outside looking in, but phosphine is a type of gas that doesn't live long on Venus. Venus's atmosphere, what it's comprised of, ends up breaking down phosphine gas and reforming into other things very quickly. Anywhere from a few seconds to a few years, phosphine can last on Venus. And our solar system has been around for billions of years. About 4 billion years, to be more precise. So you would expect, if there were any phosphine on Venus, that it would have been gone long before now. But we've been detecting a lot of phosphine in the upper atmosphere of Venus. And so scientists have found that this could mean one of two things. Either one, there's some sort of photochemical, meaning sunlight, or geochemical, meaning coming from Venus, creating phosphine that we're not really aware of any such thing existing yet. Or it could be a bacteria similar to bacteria that we have here on Earth that we know of that does make phosphine as a byproduct or as a waste product. We as humans make carbon dioxide as a waste product. When we breathe out, we create carbon dioxide. Plants, cyanobacteria in the ocean, they create oxygen as a waste product. So this is what's called a biosignature. And biosignatures are these waste products. If an alien from a different solar system were looking towards Earth and they saw that we had a lot of oxygen on Earth, they would think that Earth is a good contender for life because we have a biosignature of oxygen that really often only comes around, that we know of here on Earth, from living organisms like plants or cyanobacteria. So there might be bacteria living in Venus's clouds, which means life could be other places besides Earth. A lot of scientists really didn't think that it was impossible for life to exist other places besides Earth, but this would be the first confirmation, the first evidence of life existing on another planet, which would be absolutely revolutionary and groundbreaking. Now we have some plans. There are some plans that are that have been in the works for years before we made this discovery, to send atmospheric balloons to Jupiter to collect data. And this is kind of more of a push. This is more incentive to get there and look and find out what's creating this phosphine. Because it might not be life, but it could be. And that's enough to go there and find out. So before I end off, I want to just talk about a couple other events that are happening. One is a meteor shower that's going to be occurring this month on the 21st. A lot of times when people talk about... Did I say Jupiter?
Yep.
Why do I keep saying the wrong things? Venus. Life on Venus. Maybe life on Venus. I want to start off, before I talk about the meteor shower, talking a little bit about what makes a meteor shower. Meteor showers are bits of rock and large, maybe small pebbles, medium-sized rocks that come through our atmosphere and burn up in our atmosphere. And meteor showers end up coming from a tail of debris from comets. Comets are like dirty snowballs comprised of rock and ice mostly, and are on average the size of a small town. But most of them live in the furthest reaches of our solar system, past the orbits of Neptune, the farthest planet in our solar system. But sometimes these comets come in through our inner solar system. And when they do, that ice ends up turning into gas, and it leaves a tail of rock and dust behind the comet as it flows through our inner solar system, between the orbits of Mars, Earth, Venus. And so if that comet ends up passing through the orbits of Earth, that rock trail, we'd end up plowing through it. And that's when we get meteor showers. Now, the Perseids are probably one of the more famous meteor showers that we have. I think it's usually in August. And when we talk about how impressive a meteor shower is, we talk about how many meteors you would see per hour on average. And with the Perseids, you would see about 100 meteors per hour. So that's more than one meteor per minute. So it's a meteor shower that a lot of people make a big deal out of, because it's really easy to see these meteors. However, months are littered with meteor showers. Most of them aren't really that impressive, but there is a notable meteor shower this month on the 21st, and it's called the Orinids. Now, these meteor showers get their names based on the constellation that they appear to radiate out of. So the Orinids appear to radiate near Orion the Hunter in our sky. And Orion the Hunter, we see him in the early morning right now. And so around 5 o'clock in the morning on the 21st is the peak time that you would be able to see the Orinids. And they're not as impressive as the Perseids. It's about 23, 25 meteors per hour, so that's about a meteor every 2 minutes, but that's a lot better than a lot of the other meteor showers that you might be able to see. And one of the most notable thing about the Orinids that I didn't learn about until I was researching for this show is that, as I said earlier, meteor showers are caused by debris of comets that pass through our solar system. The Perseids are made from a comet called Swift-Tuttle, which most people haven't really heard of, even though they have heard of the Perseids. But it's, I guess, fitting, because most people haven't heard of the Orinids, but the comet that creates the debris trail for the Orinids is Halley's Comet. The famous Halley's Comet that only comes around 79 years, every 79 years rather, creates the debris trail of the Orinids that you can see in October. So it's kind of like your way of seeing little bits of Halley's Comet. Halley's Comet isn't going to be around until another 40 years or so from now. But you get to see the Orinids, which is almost as good, right? I think so. It's still good. I'm not going to say it's not good. It's great. The Orinids are great. Go out and see it. It's worth going out and seeing the Orinids. That is true. It's 5 a.m. Eastern Standard Time, or Eastern Daylight Time, So you would have to adjust that to whatever time zone you're in, and hopefully that's an area where you'd actually be able to see the peak of the ordnance. So that's on the 21st at 5 a.m. And then finally, but certainly not least, Halloween. Halloween, most people don't know this, is a astronomical holiday. It is what's called a cross-quarter day. And a cross-quarter day is the halfway point between an equinox and a solstice. Halloween is the cross-quarter day between the autumnal equinox, which we've passed, and the winter solstice. And not only is that cool, but this Halloween is even more special, because on the day of Halloween is going to be a full moon. Now, we've had moon phases that were pretty close to full moon on Halloween in the past, but we haven't officially had a full moon land smack dab on Halloween for 46 years. And we won't have another full moon on Halloween for another 19 years. So it's a good time to just kind of take that in, tell your friends when you talk about ghost stories, and how you can make up a little story about how this Halloween's going to be a little more spooky because it officially has a full moon. On top of which, October that means October is going to have 2 full moons in it. There is a full moon on the 1st, and there's going to be a full moon on the 31st. So those are some of the major things that you can see in October. Again, I always recommend, even after a show, just when you go out, look for the more notable things like the Summer Triangle with Lyra, Aquila, Cygnus, and you look to the north sky and try to find some of these constellations. There's some major, some minor, Cassiopeia, Cepheus, and Draco. These constellations are going to be up all year round, so you'll get to practice your astronomy. Now, within the next week, I'm going to have this video up on the website with bonus content and some supplementary information, including a star chart that you can use to help you find some of these constellations in your sky. I think so. I never really like memorized all the special names for the moons that we have. It's not often something that I really consider all the time. But yeah, I think it is called this. I think particularly it is a blue moon if there's 2 full moons in a month. But so check out our website, flyscienceguystarshows.com. You can find that in our Facebook page. You can go there. Again, I'll have supplementary information and bonus content on the website within a week, hopefully. And while you're on the website, look at some of the images that we post. I try to take images with telescopes and binoculars to kind of show you what you can find in your nighttime sky, even if you don't have super high-tech equipment. We also have some more shows coming up. We're gonna have a Halloween show called When the Stars Go Dark that talks about all the dark sides of astronomy, what other cultures might have done in the name for astronomy, and some spookier people involved with astronomy. That's going to be done on Halloween. November, we're going to be doing a show that talks about how to shop for telescopes if you're looking to shop for telescopes for any loved ones. I talk about how to shop for a telescope so you don't get taken advantage of by off-brand telescope companies that try to sell you certain aspects of telescopes that aren't as helpful for astronomy necessarily. And also go to the site if you like what we do and you want to see more of it and want us to keep doing it. There's a place for you to donate on the website safely using PayPal. So that's never necessary. Our content is pretty much always going to be free, but this is just helping us stay in, helping us keep doing this. But with all of that said, I'm going to open up the floor for any questions that people might still have, and I'll try to answer those. I'll be here as long as we have questions. But if you're all set to go, thank you so much for watching Roadmap of the Stars. And I always encourage you guys to come back, keep learning more, never stop asking questions about space and science and the world around you, because there is so much that we don't yet know, and so much that we can all still learn together. So I'll open up the floor now to any questions if you guys have them. And in the meantime, I'm just going to fly around and look at some of these planets. Fun fact, genuinely, my favorite planet is Uranus. Uranus is a kind of weird planet like Venus because unlike a lot of the planets, it orbits around the sun a little differently. Instead of rotating counterclockwise almost straight up and down like the Earth does, it almost rolls around on its side with its poles facing the sun, so it kind of rolls around the solar system like a ball, which I think is really funny. It also doesn't help its namesake to make it not a comical planet, but that's the unfortunate thing about having a favorite planet whose name is Uranus. A lot of people, they always try to like subvert around those names in like schools and stuff. You are very welcome, everyone. It means a lot to me that you enjoy the show. But it always bothers me whenever I mean I don't think it bothers me whenever people in schools try to subvert the funny names like Uranus or Uranus in school. But there was this one time I heard this really pretentious way of calling it Uranus, saying that that's how the Latins did, and they may have, but no one calls it Uranus. Becca's wiggling towards me. I know if she has something to say or not.
I just wanted to ask if you talk about the that you Stellarium space.
Oh yeah.
I think they're so cool.
So Stellarium, the one I use mainly for the star aspect of it, it's a free program that you can have on your computer, and it's often really helpful for I use it all the time to plan my shows. If there's something that I'm like, this doesn't look too right, I'll like go to that specific time, like what moon phase something's in during a certain time, or how close certain things are together, or how things look. And you can go pretty far. I think you can go maybe 900 years into the future or the past and see how things look a little different. It also has mobile versions too. Android phones have a free version of it that you can use, but also a paid version that you can use, which has like it uses your phone's gyroscope, and you can point your phone at the stars, and it'll tell you roughly what constellation you're looking at. It's not perfect, but it's pretty good. Can we tell if there are any planets around any stars that are not our own solar system, or or are the closest stars to us still too far away? So there are ways that we can tell that other stars have other planets around them, and what they're called are exoplanets. So I'm gonna back out here to show you. So we're leaving our solar system. There goes our solar system with our planets. And we're now in some of the nearby stars. The nearest star to us is about 24 trillion miles away. And what we find is that the way we look for planets around other stars is when we stare at a star, we either look for it either kind of wiggling back and forth slightly, meaning that there's a really massive body around it orbiting it, or if we stare at a star and a planet moves in front of the star, the light will dip. So those are two common ways that we look for planets around other stars. And it is a difficult thing to do, but we have found some. These are what are called our exoplanets, and each circle that you see now is around a star nearby that we have found planets orbiting. Now, it's not always easy. So these other stars that you don't have a blue circle around, they might have planets around them, but it's still a hard thing to detect. But every blue circle is around a star which we have found at least one planet orbiting. And not only do we know that we have found some, but from this we've learned that 1 in 5 stars has an Earth-like planet orbiting around it. Most of these planets, though, are going to be larger, uninhabitable gas giants like Jupiter. But like I said, 1 in 5 of these, it does have an Earth-like planet around us. So this is why I say that astronomers and scientists, they don't really believe all that much that there isn't life somewhere else in the universe, because there's just so many opportunities for them to have life. The program that I'm using here to do this is called OpenSpace. It's a collaborative, free open source program made by in conjunction with several Ivy League universities around the world, and I think mostly in America, though, as well as collaborative efforts of Hayden Planetarium and NASA. And so, like, whenever I show you images of Mars, for instance, we turn off the. Whenever I show you Mars, for instance, when we flew down to the planet, the height maps that they had, meaning the fact that we could see the volcano, are because of efforts from NASA and JPL. But
Okay. There was a lot about your.
There is data being collected from these objects all the time. Now, I don't have. This is kind of a general mask over these planets. I haven't found the setting where I can get the up-to-date satellite data, but that does exist in this program. But it's amazing to be able to land down on these planets and just kind of explore the terrain as if you were really there. So right now we are in Valles Marineris. We can see here's one of its canyon walls over here. So I wanted to incorporate this program because I thought it would be incredibly useful for this kind of for these kind of talks, being able to show you actual scales of things.
Clarify.
Yes. Right.
I wouldn't be able to make it up.
Oh.
See planes.
No,
Like outside of our
no,
solar
not with the naked eye. Those pinpoints of light are the stars, and planets are hugging stars so tightly in terms of like human scales that you're not going to be able to see one around a star with the naked eye. Scientists, and if you have some special equipment that you can attach to a telescope that looks for those kind of things, yes, but with the naked eye, or even just looking through a telescope with your own eye, no, it would be far too difficult for the human brain to register whether there was something moving in front of the star. But no, this was an absolute pleasure. I think it went pretty well. I don't think I looked at Jupiter. I remember being underwhelmed with the program. I wanted to do the star portion on I wanted to do the star portion on here as well, but Earth, there we go. But it was far too difficult to get everything just right. Jupiter's not that bad, I guess. I wonder what happens if I fly into. We don't really know much about the deeper atmosphere of Jupiter, because it is just a gas giant. I like go into. Probably not. It probably registers the outside as the surface. Yeah, it does. So I can't fly into Jupiter. That's a bummer. That's okay. We don't need to fly into Jupiter. I would have liked the height map for the Great Red Spot, though, so you could just fly into the Great Red Spot. Like, the Great Red Spot is like an eye of a storm. It goes down into Jupiter. You're very welcome, Melissa. You're very welcome. Well, I think in that case that might be. I'm not getting many other questions. I think we're good to stop here. So I want to thank you guys again. If you do have questions, again, you can go to the website and there's a place where you can send questions. You can even send anonymous suggestions if you feel like something should have been done differently, or if you feel like I should explain certain things a different way. There's an anonymous suggestion thing. You don't have to put your name down for that. But there's also a section where you can ask questions, and if you include your email, I'll email back to you with a well-detailed answer as best as I can, and give you some resources to learn more about whatever you ask about. But yeah, look for our look on the Facebook page and our website in the next week for the bonus content of this show. And I hope you guys have a wonderful rest of your night, and I hope that you look up to the sky and try to find some of the things that I've shown you today. This video will stay up on the Facebook page, so you can come back and review it anytime you want. So good night, everyone, and stay safe.